Morning, students. So, in the last class, we have seen what is the principle of operation of an induction machine as well as the concept of slip. That is the difference between the synchronous speed of the rotating stator field and the actual rotor speed n. So, that difference between ns, because the synchronous speed we denote by ns, so synchronous speed of the rotating stator field and the actual rotor speed n, or we say nr also, is what we call slip, and it is given by slip is equal to ns minus n by ns. So when the machine is at still means rotor is not rotating, that time n is equal to 0. So ns minus n by ns will become ns by ns. So slip will be 1. So at stationary condition, slip is equal to 1. So now we will see what is the frequency of the rotor current. So the relationship between the stator supply frequency, synchronous speed. So stator, we know that in the stator there will be slots, and the three-phase connection is given to the stator. Okay, and there will be a synchronous speed will be there. And as I already explained in case of a slip, how slip is occurring and all, and the number of poles is p. Then the frequency is given by f is equal to p ns by 120. I think ns is equal to 120 f by p. That formula will be familiar to you. So we cross multiply and we get frequency is equal to p into ns by 120. And when the rotor is stationary, that means the speed of the rotor is 0. That is nr or n. In some textbooks they refer it using nr. Some say it as n2, or some say it as simply n. Okay. So the frequency of the rotor current is the same as the supply frequency. So at the standstill condition, that is when the rotor is not moving, the frequency of the rotor current is same as the supply frequency. So listen carefully. When the rotor is at standstill condition, that is slip is equal to 1, n is equal to nr is equal to 0, the frequency of the current is same as the supply frequency. Okay, first point. Then for the rotor speed n, so the rotor is rotating. So the rotor has to hardly begin to start rotating, right? The relative speed between the rotating flux and the rotor is ns minus s. You have studied the concept of relative speed, right? Relative speed, positive will be, sometimes it will be x plus y and sometimes it will be x minus y, right? In your aptitude sessions, you might have studied about relative speed. So the the stator magnetic field, it has a synchronous rotating speed of ns, and the rotor is also rotating. Then the relative speed between them will be ns minus n. Okay, and the rotor current frequency, that is frequency at any slip, the concept of slip, the frequency at any slip speed will be given by f dash is equal to ns minus n. So when the rotor is rotating, this equation f is equal to p into ns minus 120. In that case, ns we will replace it by relative speed, and ns, and it will be f dash is equal to ns minus n by 120 into p. So f dash by f will be p into ns minus n by 120 divided by p into ns by 120. So it will be ns minus n by ns. So n is a rotor speed only. Ns minus n, that is equal to slip, right? So eventually we get it like f dash is equal to sf. So at any slip condition, the rotor frequency is equal to s into slip times the supply frequency. So f dash we call as the slip frequency. That's what we are seeing here, the frequency of the rotor current. So f dash is equal to sf. So this derivation is very important. So we can say like at any slip s. So slip s, the relative speed between the stator field and the rotor is decreased, right? That is, it will be ns minus n. Okay. So at the starting condition, I told you, like when the rotor is not rotating, slip is equal to 1. In that case, f2, okay, they say it as f2, or those say f dash, they say. So that is actually the rotor frequency. At the starting condition, when slip is equal to 1, f dash is equal to f only. And the slip frequency is equal to sf, and the slip speed is ns minus nr. So that is the conclusion from this derivation and the theory that we have seen now. Hope that is clear for you. Now we will see the effect of slip on the rotor circuit, the complete rotor circuit, what is the effect of the term S? S is slip, Ns minus N by Ns. That is the difference between synchronous speed of the rotating stator field and the actual rotor speed N. So we will see what the difference this S is going to make. So this is the equivalent circuit of a equivalent rotor, just same like the transformer only. Only thing is like the rotor side is short circuited. We already saw that. Okay, this equivalent circuit I have directly drawn. I will bring you to this point, this figure, like how we will reach the figure. Okay, this is the stator side is same only. So there is no change. Okay, so I am just focusing on the rotor side only. Even everything depends upon the rotor side. Rest everything is same as a transformer only. Okay. So this is the rotor side. So this is the rotor resistance and this is the rotor reactance and this is the EMF induced in the EMF per phase induced in the secondary. That is secondary is the rotor side and current per phase in the secondary. So at standstill condition, that is when the rotor is not rotating, we can say that the current will be EMF induced in the secondary per phase divided by the total impedance, and Z is equal to root of R2 square plus X2 square. And EMF induced in case of the EMF equation in case of a induction machine, which is similar to transformer only. 4.44 into NPH into flux into frequency into kW, and where kW is the winding factor. You don't have the derivation, you just understand the equation. Okay. And the current I2 will be E2 by root of R2 square plus X2 square. So at standstill condition, when the rotor is not rotating, S is equal to 1. So there is no concept of slip, equation of slip coming here. So standstill condition is clear. Okay. Now we will move on to the running condition. Running condition is rotor is rotating. In that case, the EMF in the secondary, that is E running, that is E at the rotor side per phase will be 4.44 into NPH running, that is speed of the rotor, into the resultant flux. The flux that we take will be the resultant flux into the winding factor, because when we are rotating, the flux will change and we'll take the overall resultant flux only. Okay, that's also not that much important for you. Your play lies here. So EMF per phase will be S into E2 per phase. So at standstill condition, it was only E2, but when it comes to running condition, the slip term will be there. So resistance that is not depending upon the frequency, so it will be R only. But the term reactance, since we can write as it is dependent upon the frequency. So 2 pi FL, so F is becoming SF, right? So you know that at running condition, F dash is equal to SF only. So running condition frequency is S into F. So S into 2 pi FL, that is X into X2 per phase, that is reactance per phase. Okay. So Z2 is equal to R2 plus JXR is equal to R2 plus JSX2. So EMF EMF will be S into EMF and reactance will be S into reactance. But resistance is not a frequency dependent term, so we need not put the slip factor. So it is equal to root of R2 square plus SX2 the whole square. So Z will be root of R2 square plus S. So see, so what will be the final current EMF by total impedance, right? So it will be SC2 per phase divided by root of R2 square plus SX2 the whole square. That is the case of the running condition. That is in the running condition. Okay. Okay. So from this figure at standstill, we finally arrived at this figure at the running condition. In that case, the EMF will be S into E2, resistance will be R2, and the reactance will be S into X2. And here the frequency of the supply will be S into F. Okay. So we can write IR per phase is S into E2 by per phase, same only, R2, root of R2 square plus SX2 square. Now we divide numerator and denominator by S. So we get E2 per phase divided by root of R2 by S the whole square plus X2 square. And we will see why we are doing it. Okay. And we can also say that the angle at which the rotor current lags E2 is tan inverse X2 by R2 at standstill condition, and at running condition It will be S into x2 by R2. It will be tan inverse of x into x2 by R2. That is the angle at which the rotor current lags E2. E2 is the induced EMF in the secondary, and R2 is and how much the rotor current lags. It can be at standstill condition. It will be tan inverse x2 by R2. The same concept we have in case of transformer also. But when we consider the running condition, we have the slip also. So it will be tan inverse x2 by R2. Okay. So since we rearrange the equation like this, EMF, so we from the EMF we remove the slip factors. So from the reactance as well as EMF, we remove the slip factors, and so we are making it independent of slip. Because this we are doing to convert the source to supply frequency. Earlier in this equation here it is the slip frequency. Now by taking common and making R2 by S, we now converted to supply frequency. So this is same only. So this will be E2 for phase, IR, X2 and R2 by S. And now we add and subtract R2 to R2 by S. So R2 by S is equal to R2 by S plus R2 minus R2 is equal to R2 into 1 by S minus 1 plus R2. So R2 is the rotor resistance, and R2 into 1 by S minus 1, that is the electrical equivalent of the mechanical output. So R2 into 1 by S minus 1 is the so R2 into 1, that term we call it as the electrical equivalent of the mechanical output. So you will understand better, you will understand more about this. And R2 is the rotor resistance. Okay. So finally we arrived at this equation. So this particular term R2 by S is converted to R2 into 1 by S minus 1 plus R2. So eventually we get the rotor circuit, equivalent circuit like E2 per phase, R2 is there. So this R2 came from R2 by S, and R2 into 1 by S minus 1. So this adding these two, we will again get R2 by S only, and we have the X2. So this is the supply frequency only. Okay. Now we will see a different condition. We will see when S is equal to 0, that is when the slip is equal to 0. So 1 by 0 is infinity. So this complete term will be infinity. In that case, the rotor current is 0, that is torque produced is 0. So when slip is equal to 0, the torque produced is 0. This derivation is very important. So now slip is 0 because we are drawing a torque slip cara. So this is very important. So when slip increases, that is the term. So this denominator term is increasing. That means R2 into 1 by S minus. So denominator is decreasing means the total will be less only. So 1 by 4, 1 by 5, 1 by 6 we see means the total value is getting decreased only. So this completely will be decreased, and as a result, the current increases. That is the power output increases, and that there will be a torque output. And we have the equation for the rotor input, or we also call it at the air gap power, because it is transferred from stator to rotor through the air gap. So that's Faraday's law, electromagnetic induction, Lex's law, everything they follow. And due to the relative motion, the power will be induced. The power will be transferred from stator to the rotor through the air gap. So we call it as the air gap power also. So rotor input is equal to 3 into IR square, IR the whole square into R2 by S. That is only R2 consumes active power. Okay, only R2 consumes the active power, because we need not consider. You will get a doubt. Why are we not taking the X2 term also when we consider when we are considering the rotor power? Because all active power is only consumed by R2. So the rotor copper loss will be 3 into IR square into R2. Sorry, here it is actually R2 by S only. R2 by S. So this is R2 by S. Okay. 3 into IR square into R2 by S. This is the same equation. Okay. Okay. So the rotor copper loss is equal to 3 into IR square into R2 by S. Okay. So the gross mechanical power developed is 3 into IR square into R2 into 1 by S minus 1. From here, this equation. R2 by S, we write it as R2 into 1 by S minus 1 also, right? That is the electrical equivalent of the mechanical output. So that equation we substitute here. Throw 3 IR square into R2 into 1 by S minus 1 will be here. So the net mechanical power is equal to gross mechanical power minus the mechanical power that is lost. So this is the gross mechanical power minus the mechanical power loss. Okay. Okay. Now we will find a very interesting relationship. The rotor input power is to rotor copper loss is to gross mechanical output. So we have expression for everybody. Sorry. The rotor copper loss is 3 IR square into R2 only. Sorry, I'm sorry. So this is rotor copper loss and this is rotor input. I'm very sorry. Rotor copper loss is not depending upon the slip. Actually, I thought this rotor input is same as the rotor copper loss also. Sorry. So this is the rotor input, that is 3 IR square into R2 by S, and this is the rotor copper loss. This is 3 IR square into R2. This is by S is coming because it is depending upon the slip, and this is the gross mechanical power developed. So eventually, when you are taking the ratio between the three quantities, we get it like 3 IR square into R2 by S is equal to 3 into IR square into R2 is equal to 3 into IR square into R2 into 1 by S minus 1. That is 1. So when we can remove the common terms and cross multiply, then we get it like 1 is to S is to 1 minus S. Okay, that is rotor input power is to rotor copper loss is to gross mechanical output. That is rotor input is to copper loss is equal to gross output is equal to 1 is to S is to 1 minus S. So we saw that the rotor copper loss is equal to S into rotor input, right? So this time into S will be the rotor copper loss. That's why we conclude it like rotor copper loss is equal to S into rotor input as well as gross mechanical output is equal to 1 minus S into rotor input. 1 minus S into rotor input. So rotor copper loss is equal to S by 1 minus S into gross mechanical output. So the approximate efficiency is given by gross mechanical output by rotor input by 1 is equal to 1 minus S. Substituting you will get. So we can write like 1 minus S, we write it as slip. So slip we substitute like N minus N by NS. So eventually finally we get it like approximate efficiency will be equal to N by NS, because efficiency is the gross mechanical output, how much mechanical output we are getting by rotor input. So that is actually 1 minus S from this derivation. Okay. So efficiency is approximately equal to approximate rotor efficiency is N by NS, and this is how you derive it. Okay. I hope that much is clear for everybody. So finally we are at this equation. The rotor side it will be S E2 per phase, R2, SX2 and SF. This is the slip frequency, the equivalent circuit in terms of the slip frequency. So from there we substitute like E2 per phase is equal to IR into X2, and this we made it as R2 by S, and then adding R2 and subtracting R2 we get it like E2 per phase is equal to R2 X2 and R2 into 1 by S minus 1. So we have seen that overall resistance, overall rotor current is increasing. When this term decreases, IR will be increasing. We saw that in the earlier case. Now next what we have is the torque equation. So the next concept is about the torque equation. So the torque equation, we know that equation for torque, the mechanical power developed is equal to 2 pi nt by 60. The basic equation of torque, any rotating torque, rotating force, when we consider, the equation will be the mechanical power developed will be Pm is equal to 2 pi nt by 60, where n is equal to speed at which it is running. So n is the speed at which it is running and torque is the overall torque. So torque can be, so if the torque will be like 60 by 2 pi n into Pm. Pm is the mechanical power developed. Okay. So, and here P is the gross mechanical output, yes, and T is the gross torque developed by the machine in Newton meter, and N is the speed of the rotor in RPM. N is the speed of rotor in RPM. T is the gross torque developed by the machine in Newton meter, and P is the gross mechanical output. So T we can substitute like 60 by 2 pi N is equal to mechanical power developed. So in the previous section we described like mechanical power developed is equal to 1 minus S into P2. P2 is the rotor input. Why it is given P2 means 2 means the rotor side, secondary side. So T is equal to 60 by 2 pi N into 1 minus S into rotor input. That is equal to 60 by 2 pi N into 1 minus, so S is the slip, N minus N by Ns into rotor input. So P2 is the rotor input, okay. So T is equal to 60 by 2 pi Ns into rotor input. That is T is equal to P2 by 2 pi Ns by 60. That is torque is proportional to rotor input power at the synchronous speed. So you will be asked question, derive that rotor is proportional to, the torque developed is proportional to rotor input at the synchronous, that is T is equal to P2 by 2 pi Ns by 60. So rotor input is equal to 2 pi Ns by 60 into T. So this rotor input is also known as synchronous watts. Why we said synchronous watts? Because it is the rotor power at the synchronous speed only, and that is proportional to torque. That's what we derive now. So synchronous watt, that how we can say that synchronous torque is that torque which at synchronous speed develops a power of 1 watt. So T is equal to 60 by 2 pi Ns into rotor input. What is the equation for rotor input? 3 IR square into R2 by S. Okay. IR is the rotor current, R2 is the rotor resistance. So T is equal to 60 by 2 pi Ns into 3. So we have an equation when at the running condition resistance IR is equal to SC2 by root of R2 plus root of R2 square plus SX2 the whole square. So IR is equal to SC2 by root of R2 square plus SX2 the whole square into R2 by S. So T is equal to 180 by 2 pi Ns into SC2 square by R2 square plus SX2 the whole square into R2, because squaring, substituting mathematics, okay. So here we can see that T is proportional to E2 square. So you know that in a transformer or induction motor, the secondary current will be E2 square. It will be proportional to E1 square because we considering the turns ratio, and that is also proportional to the supply frequency. So eventually we saw that T is proportional to E2 square is proportional to E1 square is proportional to V1 square. That is the supply voltage. Okay, one condition. So now let's see when for low values of slip, that is the value of slip is very less. So when the value of slip is very less means this we can avoid. So 0.0001 into some reactance, this will be very small value. So XS2 the whole square will be very less. In that case, the equation for torque will be T is equal to 190 by 2 pi Ns into SC2 square into R2 by R2 square. That is 190 by 2 pi Ns into SC2 square by R2. That is T is proportional to SC2 square by R2 is this is the secondary EMF is proportional to supply frequency also, no? So we can substitute it like it's proportional to SV1 square by R2. So we can say that the torque has a linear relationship with slip, that is T is proportional to S, like that is if slip increases then torque increases. So torque to be constant, SV1 square and R2 also should be constant. Because R2 is a constant value, supply frequency is constant, and overall this should be constant. Then we can write like S into V1 square is like slip into supply frequency in the primary side will be equal to slip in the supply frequency in the secondary side. Because when the terms are constant, we can equate them, right? So S1 V11 square is equal to S2 into V12 square. One example I will say. An induction motor, it has a supply frequency of supply voltage of 440 volt, and it is rotating at the rotor is rotating at 950 rpm, and it has a synchronous speed of 1000 rpm. If the voltage is changed to 400 volt, then what will be the rotor speed? So we can use this equation S1 V11 the whole square is equal to S2 into V12 the whole square. So slip we can find out because we have the synchronous speed. So slip we can find out. So what we need is S2. So we substitute and we find out what is the value of x2. And we have n is equal to 1 equation for slip you have. S equal to ns minus n by ns. Substituting in that, you get the value of the rotor speed. Now we will see the case of large value of slip s. Large value of slip s means sx to the whole square, this term. This will be very large so that we can neglect the other term. That's what we are doing here. Sx to the whole square we are neglecting here. So torque will be proportional to sc to the whole square by sh to the whole square only. Because R2, it became very small when compared to s into x2 in case of high slip value. In that case, it is proportional to the final equation. We get it like t is proportional to 1 by s. So at low value of slip, t is proportional to s. At high value of slip, t is proportional to 1 by s. So for a stable condition, t is proportional to s. That is at low value. So if load increases, speed decreases, slip increases, and Tm also increases. But when t is proportional to 1 by s, load increases, speed decreases in that case. Then the slip will be more, then Tm will be less, and the overall mechanical torque will be less than what is the torque required. And in that case, it will be the unstable condition. Here, the overall mechanical torque is equal to Td. So, it's a stable condition. So, this is the torque slip chiara. This is a stable operating condition because here T is proportional to S and here T is proportional to 1 by S. So we can know the impedance triangle also. We have SC2, R2, SX2. So this will be R2, this will be SX2, and this is Z2. So I2 will be SE2 by root of R2 square plus SX2 square. And similarly, power factor cos phi 2 will be equal to R2 by root of R2 square plus SX2 the whole square. Also, the torque equation is proportional to E2 into I2 into cos phi 2. That is the torque equation. So, T is proportional to E2 and I2 will be SC2 by root of R2 square plus SX to the whole square. And the power factor will be R2 by root of R2 square plus SX2. So, everything you know from the equation. So, T is proportional to SC2 square by R2. So, same equation we are right. Torque is equal to K into SC2 square by R2 and R2 square plus Sx to the whole square. K is the proportionality constant and that K is equal to 180 by 2 pi ns. How you got? That's why I explained this for you. 180 by this we derived, no? So this value is the K. That is the proportionality constant. So finally we arrive at the equation for torque. Okay. So I think everything is clear for you. How the journey that we had from the dependence of the rotor frequency, then we got it when we reached f dash is equal to sf, then the torque equation, then we reached the what we call the torque slip chiara. So I hope everything is clear for you. I shall clear your doubts in the live session also if you have. This is actually a bit lengthy video, but be patient and watch it because this is the need of the hour. Okay. Thank you.